I said that's the big question. So
Yeah,
that's how lucky for us.
it's a lot of time.
I won't question on
And the
the
what?
the dog for like 2 hours. More than 2 hours. Like it's taking up time.
And the what word? I give up on the second major. We have the original.
Oh,
Yeah.
I mean, I think I'm gonna give myself a little bit prior to.
No, I just give up. Honestly, I have a lot to do.
I mean, that's true. Is it-
Like I
it's
took 2
5%?
hours and I had like I think 6 or 7.
Let's start. Zoom people, if you have a question, please use your mic, but I will also check the chat. All right, so yeah, the midterm is this Friday. It's mostly stuff before diagonalizable, but there is a question of sub-adjoint, and there's also a question of diagonalizable, but it's not a big question. It's not, you just have to know what the statement is. So let me go over the statements. So first we talked about, we put this result that if you're over the reals, you're diagonalizable if and only if geometric equals algebraic, and the sum of the algebraic equal to the whole space. Okay, right? So we have this result. And for complex, why did we only need the first part and not the second part? Just, I want to see what people do. Why did I don't need the second part? You have to know, so I have to ask you. Zoom people, do you know why we don't need the summation? Yeah, I'm not going to. Okay, good. No, I'm going. You know, I want to see one of the other people. You three always talk. Zoom people, can you tell me why do I need the sum? Why I don't need the sum for complex? No. You can use the chat if you like. Yes. Can you tell me? You know? Okay, yeah, go ahead. Yes, well, I forgot his name. What was his name again? What was your name again? Oh, yeah, go ahead. What is it? Right. So, we have a geometric characteristic polynomial, and you factor it in lambda minus lambda I to mi. And FTA says that polynomial completely splits. So all the roots of P are in C. So if you're n degree, you will have n roots. So fundamental theorem of algebra. C up to a multiplicity. Okay. That was one. Another one is the result we proved. Oh, because we also, okay, yes, thank you. Over real or complex, sub-adjoint is the same as diagonalizable with an orthonormal basis. Okay. One point that gets forgotten is that you need this to go from left to right, because there are matrices that are diagonalizable but are not self-adjoint. And I will do an example in 2 seconds. Same thing for normal. Diagonalizable if you only have normal. But again, you need orthonormal basis. So there are matrices that are diagonalizable with non-orthonormal. So if you compute the eigenvalues and eigenvectors, you can diagonalize it. But the problem is these two vectors here are not orthonormal. Okay, so -1 dotted with 1, 2 is 1, right? Okay, I'll do it. -1 times 1 plus 1 times 2 is equal to -1, which is 1. So it's not 0. So they're not orthogonal. No, it's not even orthogonal. No, it's not. Oh, it doesn't matter. You could have written orthogonal. It doesn't matter. You can just divide by the norm.
All orthonormal are orthogonal, but they're unit vectors, right?
Or what?
Or orthonormal bases are orthogonal bases of unit vectors.
Yeah. So, right. So VI is perp to VK, and the norm of VI is 1. Okay. So this is all we got the last 2 or 3 weeks. Okay. So if you have a question, please let me know. Yes.
So the -1, 1, and the 1, 2 are like eigenvectors of the transformation.
Of this matrix, yeah.
Oh, well, yeah. And is it like order? Like -1 is the eigenvalue of the -1, 1, and then 2 is the eigenvalue.
Yes. Otherwise, it doesn't work. You have to match column, first eigenvalue, second. Yeah. So. Going once, twice. Right. Let's see. So over C, we proved the following result, that you can always find a orthonormal basis, so that T of that basis can be written as eigenvalues and stuff. For the next 2 weeks, we will extend it to matrices of this form. So mainly, it will be blocks. That's why it's called Jordan block. So you will have stuff like, lambda 1, lambda 2, lambda 3, 0, and so on. So any ones and zeros, any ones will be right on top of the diagonal, and the rest will all be 0. Okay, so it's very localized. Think of like a band. It's like a band of stuff and then 0. Okay, that's Jordan block here. Then we will prove it over C for any linear map. And we will also prove it over R given this summability condition. So that's why this summability is very important. It shows up all over the place. So we have this condition that summation of mi. Yeah. So if you have this, you end using this, you will get upper triangle. Even though you will not have, so this is over reals. Even though you don't, you might have that geometric is strictly less than algebraic. Okay. Yeah, so we already did the complex case. Now we have to do the real case. And we will need an object called invariant subspaces. You start with the map and the subspace in V, then you call W invariant if, or stable, if you can map W inside W. So the picture is W, and here's V, and then make it bigger. And here's W again, and then it sends it inside. Okay. That's called being invariant because you stay within the space. I mean, this is from physics. Meaning you stay localized in some region, some local optimizer. You don't escape your local minimum. Yeah, so this shows up in many places. And one of the reasons is because eigenspaces are invariant subspace. They are the canonical example. So, because if you give me a vector in the space W, then I have that TV is still in the space W. So more formally, T of E lambda is inside E lambda. It's in fact equal, but one is right. Okay. So that's T invariance. That's one example. Let's do another one. Take V to be polynomials. Your map to be the derivative map, and then take W to be nth degree polynomials. Can someone tell me why W is T invariant? Yes. Of what degree? Yeah, so here we're using that if P is in Pn, then P prime is in Pn minus 1, which is inside Pn. So indeed, T of Pn is inside Pn. Okay.
Notation for the course, writing, subset and then a little dash underneath. That just means it could be, right? Like we're not saying.
Yeah, we don't know, right? Yeah, it means you have to prove them because you're saying that they can never be like in your homework for nilpotent. Yeah, so in your homework for nilpotent maps, you have to prove not equal. So it's extra. How about this guy? Is W invariant for this? can do like this, you can nod your head up, down, or like this. No, right? Okay, thank you. Okay, we found a way to communicate. All right, good. So, right, because if P is in Pn, x of Pn is in Pn plus 1. And so T of Pn has no relation with Pn, because you could have been sent to another one. So one is not contained in the other. They only overlap. So they only overlap. All right, here's some results you are free to use. If U is T invariant and invertible, then it's also T inverse invariant. And let me prove that. So, what are we saying? Yeah, we're saying T of U gets mapped inside U. And then, let me just do it. And then, you say the same for this. So, wait, now I know. So this is a tricky one. So you have this, but since your guy is invertible, you can in fact say that they're equal. Now, I mean, if you can tell me why, that would be amazing. If you know, you can guess. Yes. Right. So, yeah. So, since you have this result, you can consider the restricted map, T restricted W, and this guy, call it S, sends W to W. But exactly, so you have dim of U is dim of image of T restricted W plus dimension of the kernel of T restricted W, but this guy is 0 because you're invertible. And so you get this, which is just this. You get that the image dimension and the dim U, they're equal. So they're the same subspace. And from here, you just take inverses. So indeed, U is T inverse invariant. Okay. Happy? Beautiful. Another nice one is that if U is T invariant, the orthogonal complement is T star invariant. So the proof is easier than you think. So let me do it. So what do I have to prove to you? I have to prove. Yeah, I have to prove that T star of U perp is inside U perp. Okay. In other words, I have to prove that if you take W in T star U perp, then W V or U is 0 when U is in U. Okay? So these are the same thing. And then let me move a little bit here. But then what does that mean? It means that W being in T star U means W is equal to T star V, some V in U perp, right? So you have T star V, U, let me do it the other way. U T star V, and then what do? You do with your hand, I do it like this. But then I know that TU is inside U, so how can I finish from here to get 0? Just to see if you follow the implications and yeah. Yeah. Okay, so because TU is in U and V is in U perp. So, okay. Yes,
Whenever we talk about like curve, are we automatically assuming that it's a linear product space?
Yep.
As about the
Yep.
linear product?
okay. So you can use this result now, free. So you whenever, yeah. How do we use it? If you find a creative way, please let me know. Zoom people? Okay. What else? All right. So let's prove that criterion. Namely, this is really for F equal to R. That's what we're thinking here. Because for complex, we did it last week. So you take your map, you take your basis, and we'll show that T is upper triangular if and only if each of the subspaces is T invariant. Okay, so TWI is inside WI. So I'm going to put that down. And because we're going to use this later, all you're trying to find is a chain, W1 to WK, where each of them is T invariant. If you do this, you get upper triangular. Okay, so we're going to use this all the time for the next 3 weeks. Just variations of this. And you already saw it within your plotting map. So we'll come back to your plotting next week. So all this stuff will get recycled. All right, so let's prove this. I think this is the easier one. So assume upper triangular. Then we have this. So why is that? Let me explain. So let me put TB1. So you have lambda 1, lambda n and stuff. And this is TB. So it's upper triangular. But then what are the columns? The columns are TB1, TBM, right? These are the columns. And you can see that this guy is TB1 equal to lambda 1 B1, TB2 equal to lambda some stuff, whatever that stuff is. Let me call it A12. Over here, B1, and then A22, B2. Okay, and so on. So each time we just adding one more term. So that means, in other words, if you evaluate BK, on the right, you will always have BK being the last one. There's no BK plus 1. So that's the same as being upper triangular. Okay, zoom. And then, yeah, how do you finish from here? How do you show that these WIs are T invariant? Okay, fine. So this guy here is in WK, right? And then, right, so you have TB1. So now, okay, I have to prove to you that TWK is inside WK. That's what I have to prove. But give me any X in WK. We can write it as summation from M1 to K of CM BM. Okay? So step 1. But then take TX. This is CM TBM. And you do it as follows. So you have C1 TB1, CK TBK. This guy is inside W1, which is inside WK. The next guy is inside W2, which is inside WK. And this guy is in WK. But then WK is a subspace, so this whole thing, so the whole thing is in WK. Okay. All right. Is that okay? All right, so that gave you this direction, namely that the subspaces are T invariant if you're upper triangular. But then if you start the other way, suppose you're T invariant, that means what? So if you take one of these PKs in WK, then you have TPKs in WK, which is the span of these guys. So there exists some A1I, so that TPK is equal to this summation. Okay, because you're in the span of them.
Professor, I have a question.
Yes.
Aren't all transformations with the same domain and codomain, like the transformation invariant?
So I did an example, right? Remember I did TP equal to XP and take P to be in PM. Then TP is in PN plus 1, which contains PN. So W equal to PN is not T invariant.
Oh, right, yeah. Okay, yeah, that makes sense. Thank you.
All right, so that's the criterion. Okay, all right. What did we prove? Right. So again, let me remind what we just talked about. In order to have diagonalizable over the reals, you need the second condition. Okay, so you need the second. Over complex, you only need this guy, but here you need both. Only this in F equals C. Okay. So it turns out the same thing will work here. So take a FT space, take F to be really the reals. That's what we're thinking, but it works for general. Then T is upper triangular. So I wrote this as well because you will see it in the book. So T is upper triangular if and only if the characteristic polynomial has dim-B roots in the field F. So let me write this in different ways. You will also see the language PT splits over F. And you will also see the one I just wrote, summation of MI is equal to dim-V. And they're just telling you that, okay, let me write another way, that this guy is P of lambda I, where lambda I is in F. Okay, these are all the same. So you can move around local stuff. All right. All right, let's prove it. Yeah, so when the field is complex, this assumption is trivially true by FTA. Okay. So you need this result, this assumption, because again, when you take the reals, there are matrices that have no real eigenvalues. So in other words, PM does not split. over F. Okay, so it does not have NV roots on the field F. It has none. The eigenvalues of this guy are plus minus I, which are not in the reals. Okay, but you can still, yeah, but over C you have a you can have diagonal representation. Okay? So this is what we proved, spectral theorem, because I did this last week. M, yeah, M star is equal to M star M. It's a normal operator. If you add twice, you get the identity because it's the rotation by, remember, pi over 2, and then you rotate back. All right, let's go. Oh, I do another example. Okay, good. Okay. Oh, actually, so you take this matrix, and I will show you that. So this is not upper triangular because you have this 8 at the bottom, but I will show that it can be upper triangular, and the reason it can be is because the characteristic polynomial completely splits, right? So V is R3. So you have 2 plus 1 equal 3, summation of multiplicities. Okay? So you have your condition, same as in diagonalizable. So that implies that A can be written as upper triangular. Okay, so, right? So let's do that. First, you find the eigenvalues, so 1 and 7. Then you find the eigenvectors. So I'm not going to do that because it's 3 by 3. It'll take a while. So you only have two eigenvectors. So let me ask you. I think I asked the question. So is it diagonalizable? Why not? Yes. Perfect. So here we have dimension of E1 is 1, which is triple less than M, which is triple less than 2, which is M1. Okay? Perfect. So now, but you are right, but it splits over the reals, and then the result we can prove shows that there exists another vector. I found it explicitly, and I formed the columns and all that stuff. And indeed, I get that you can go from A to an upper triangular representation, or what we call Jordan block, because you say it's in the Jordan block form. You only have stuff above the diagonal. Okay. No, I found this. So you basically have to find the orthogonal complement to B1, B2. No, because this is, well, actually you might. I mean, it's not a tricky one because you have two vectors and you use the dot product. Yeah. Yeah. So, okay, let me see, what do I want to say? I mean, okay, I'm gonna show it in the proof, how we find it, so we might as well, because, right, this case, yeah, you need orthogonal, and, what else do you need? Yeah, it's basically like eigenvectors, so, yeah, anyways, we'll go through it. We'll see. Because we make a concrete choice. Right, so we need the first lemma. Let's see. Yeah, so if W is T invariant, then you have that the determinant of T restricted W minus lambda I divides determinant of T minus lambda I. Okay, so I'm going to prove that as polynomials, like Euclidean division, meaning you can write, I mean, I'm going to do it right now. So you start with PT, you pick a basis for W and you extend it to the one for V. And then, let's see. Right, so we proved that W being T invariant is the same as the matrix TW of B is upper triangular. Okay? Yeah, so it means that, so the first columns here are T minus lambda I evaluated at W1 all the way to WK. These are the first K columns. And the N minus K are the rest. So you just evaluate WK plus 1 to WN. So now let me ask you, what does the determinant formula tell you? So let me write it like this. This A, B. So this is equal to what determinant? We did this like, what does the cofactor expansion tell you? Well, okay. What do you think it equals to? Huh? So what? Yeah, exactly. So whenever you look at these matrices, you should think of 2 by 2. It's the same thing. So this would be determinant of T minus lambda I BW times determinant of B matrix minus determinant of A times determinant of 0. So this guy is out. So you're left with these two. Okay, so that shows that PT is equal to P restricted W times some matrix B. So one divides the other. Okay? Zoom people? Right. So that's one lemma. And yeah. Here's another lemma. So this seems a little bit weird, but you will see why we need this in the proof. So here, this is how the book organized it. So I want to follow the book like this, since you're going to read the book. Okay, again, so PT splits, that's what this means. So if you want to think of reals, just think of PT being the product of reals. And take W to PT invariant. Then we're going to show the following technical result, that you can find some element X so that X plus W is T invariant. So T of X plus W will be inside X plus W. Okay. So let me explain a little bit why we need this. Later on, we need to build an induction, a chain, W2 all the way to Wn. And all this will do is we will start with W1, and then we will build W2 out of X1, W1. And then we will build W3 like this. So we will keep adding one element at a time, and we just need to show that there is some extra element. Right? That's all what's happening. We just need to build this chain one vector at a time. And if you want more concrete, this next side just eigenvectors. Okay? This will just be the eigenvectors of T. Okay. Right. Let's go. So again, let me repeat. We have this guy's T invariant. We will prove that there exists X so that X plus W is also T invariant. Okay. So take a basis composed of the one for W and the one for its complement. W complement, if you haven't seen it, let me write it. So WC is just all the elements V in V such that V is not in W. Okay. It's really easy. All right. So going back to what we just did 2 seconds ago, since W is T invariant, you can split your matrix into this representation. So you have a matrix and then you have 2 blocks, okay, A and B. So let's look at what happens. There's more information here. We just call them A, B, but you know a lot more than that. So let's see what we know. And we have to use a little bit of machinery called projections. So I will use projections to rewrite this matrix. Let's do that. So PW, okay? This guy takes an element in V into W. Yeah, I want to write you the representation, even though, because you might see it. So this is V BK, BK squared, and BK, M, and BK orthonormal. Okay, that's the formula for projection. Another relation you might see, so please review it. PW is equal to P. So please go review that. That's also very important. Okay. All right. So we use this projection to understand this second part of the matrix. Once you have the projection of W, you have the projection of the complement. Or if you like, orthogonal complement. What do I want to say? Yeah, so we did this map, and this map is interesting because in a sense is W complement invariant. Okay, so let me explain why. So you take W complement, but this is some guy in V, right? So nobody cares about that. But then this guy maps all the V stuff to W per. So let me do it this way, and then IPW takes you to some W perp. Okay, so in a way, anyway, so that's what we're using. We're using that no matter what the input is of the projection operator, it always maps into the complement. Right? So you take any V, it always maps to W complement. For all V and V, okay? So namely take V to be TW perp. It doesn't matter. But we just need this invariance. Why do we need it? Because then you have that this block matrix at the bottom would be upper triangle. So because SW perp is inside W perp, we have that this guy is upper triangle. From the stuff we just talked about. Okay. All right. And okay, that's good. So what's the punchline here? Yeah, so let me write the implication. So the implication from here is PT, this is PT, is equal to the thing we just talked before. So you have P, T restricted W, and then P of S. So you have this nice clean formula. And we're going to use that P of S is a product of diagonal entries. So yeah, one step at a time. This is a long proof. All right. Our guy splits. So, and we have this formula. So since it splits, what can you say about PT? Just to see if you remember the definition. What does it mean? Splitting. Wait. Ismail? Do you know? No? It means you can write it as lambda minus lambda I for lambda I in F. All right, and then meaning there is just lambda x and v. So since we have them to be in the field, there is just at least one, and that's the choice we're going to make. Okay, so we said there is just an x, so we just take the eigenvector for t. Simplest choice possible. So again, we have t x is equal to lambda, or what do I want to say here? Oh, I see. Okay, yeah, this is a little bit tricky, so let me explain. So again, we have PT lambda, call it lambda star for a second. So we have lambda minus lambda star to some n and some polynomial. But we just showed that this is also PT lambda restricted to W in times PS. So here's the trickery. Okay? We just said that you have Euclidean division for blocks. So that means you have PS lambda is equal to, PT divided by PTW. In other words, you have this is a product of lambda minus lambda K for K1 to M. Okay, so let me put all the lemmas together again. I want to show you that since PT splits, the same is true for PS. That's what I want to prove. Okay, we just proved the lemma that PT restricted divides PT. So by previous lemma, we have the PS divided by PTW is equal to some other polynomial, which we can still factor because you know what PT is. Okay, so this is from the previous lemma. I cannot do this unless I know that the thing divides the top. Otherwise, I'm dividing by like 1 over x squared and stuff like that. So that's why I'm using the previous lemma. Okay. But then, yeah, that shows that PS splits has only f roots. Okay. Okay. So, okay. So let's finish this. Actually, yeah, let me just finish it. So that means S has an eigenvector with real eigenvalue. Okay. And this guy was S. So you have this is equal to this. And I just rearrange this, so you get Tx is equal to lambda x px. Okay. Right. And right. So let me finish. So how to show from here that if you take V in the span of these two, you have that T of V is also in the span. So how do you show that? Based on this. Yes. Yeah, okay, let me, because okay, we're all over time, so I'll do it. So V is equal to Cx plus Y, Y is in W. So you have TV is equal to CTX plus TY. And we just showed that this is equal to C lambda X plus PWX plus TY. This guy is in W plus span X, all this. So it's in here, right? But then W is T invariant. So this is also in W. So you get that the whole thing is in here. Okay. All right. No, it only guarantees in company because they might not be, yeah, they might not be orthogonal. Like they might not be, they might have overlaps. The I minus P. Because so I mean you will see this. There's a thing called orthogonal projection and projection. Orthogonal projection is when you use the basis, orthonormal basis. Projection is when you just use basis. So when you just, so remember that I wrote summation in a dot inner product. No. So any basis. Yeah, that's called a projection. But we haven't really done it, so it's only for this proof. So, but it's good to go review at least this P square equal P relation. Please go review it. Yes.
Thank you for all.
Yeah. Yeah.
Definition,
In what?
like we have to write.
Oh, yeah, yeah, yeah.